Hello, everybody. Welcome. 2.007.
Now, 2007 is the introductory design course. Before doing this course, students have been through a course called 2670, which is taught in the winter, actually in the month of January, where they learn how to manufacture. They learn, they learn to use a CAD system called ProEngineer. They learn how to use milling machines, lathes, and they make little Stirling engines.
Okay, my name is Alex Slocum. I'm professor in charge of the course, and we've got a whole herd of staff and faculty to work with you guys.
They have a little bit of background in analyzing, but they don't have much background in actually designing a new product.
The first day of class in lecture, he showed us the table, and he gave us a synopsis of how it's going to operate.
So in this course, you're going to learn the design process, how to use physics, how to create real machines and designs that actually do stuff. Okay, so everything you've been doing in your life today with math and physics, we're going to turn into reality and show you how.
2007 is a very formal course.
Here's the contest table. It's the contest volcano in honor of all those joyous volcano movies that have been out.
A semester of 2 lectures per week, 1.5 hours each.
This course is very much run like a project in industry. We'll lead you through the whole course in a number of phases. Each phase to be just like as if you were an engineer at a company, either working individually or in a team, to create a real product in no time, with no resources, for no money, to sell lots of them.
So it's a full contact sport, if you will.
Let's look at the kit. Big chunk of Lexan plastic. So if your machine is faster than a speeding bullet, it won't break the Lexan. But if you drill a little hole in the corner and pull a little bolt force, it'll break right off. Okay? Wood is fantastically strong in some directions where the grain is. It's anisotropic. Okay? Remember, when you're designing your structure, a tube, a closed section, is very strong. Half a tube is not only half as strong. Okay? So, okay. More wood, more plastic, more belts, more plastic, foamy thing, more aluminum, floppy disks, adapter plate for big Ford windshield wiper motor. So this is where the calculations you do are going to have to be very, very carefully considered, because the motors will do this to improperly designed stuff.
I'm going to quickly go through the tables, and I will tell you what's going on here. First of all, the machines, they can only be built from certain parts, which we give to the students. And they have a size requirement, and this would be the box. It has to fit within the box. This is the volcano, or volcano, how Alex called it. It has a flow rate of roughly 5 volts per second, and we have that running for 40 seconds. Also, the students have power for 40 seconds. And within that time, the students collect balls, as many as possible, and then dump them off. So the contestant on the yellow side can start anywhere within the marked area. He cannot clamp himself to the table in any way, and he cannot touch the sidewalls. He cannot extend past this line here. For every ball that they drop off in this lower hole here, it's a little smaller and it's also level with the table, they get 1 point. And for every ball dropped off here, which is a little bigger but it's higher up, they get 2 points.
We said we're going to run this course like a business. And y'all are engineers, and you're supposed to create a product for the customer. I happen to be the customer. And we find that people create better when you give them a schedule, give them deadlines. Every week, the milestones exist, and the milestones are actually the output of a problem set for the course. So we very carefully lay out the schedule. 1/3 is wild, creative, wowie-zowie thinking. 1/3 is physics, details, engineering, creating the drawings, and 1/3 is in the shop making the product, and that's a really, really nice, healthy mix.
I think the biggest challenge to them, to a large extent, is doing it in a methodical way. We are not trying to give them the creativity they bring. What we're trying to give them is structure.
Let's say that the students, like people everywhere, have an intense need to create. And what we do is we take this need to create and we add physics, we add kit materials, we add lectures that teach them how to use physics and kit materials. And we put all this in this large pot and we put it in the 2007 oven and we let it bake.
We start with how to design, how to do conceptual design, how do you capture the functional requirements of a design, how do you select concepts and weed out bad concepts.
One of the things that I tried to do from the very beginning was think of every possible strategy that someone else in the contest might possibly take. And once I had all of those listed, I could begin to look at which strategy would dominate in the end. And I decided that a combination of offensive and defensive would work best.
I was after a machine that would really challenge my design ability and my ability in the machine shop, and that would be sort of different and would get attention.
I think if you're designing just to win, you probably won't win. I think if you're designing to play, then you're much more likely to win.
Well, right now I'm trying to choose between designs. I've got 3 or 4 that could possibly work, and I've just finished drawing up 3 of them that I was thinking of doing. The one that, of course, I already have a love for, and 2 others that have worked in the past and might work here.
Everybody in the class has the same task to perform, but they've all had come up with a myriad of different strategies.
Sort of gutter.
The ball deflectors.
Basically an arm.
The dump trucks.
It's a wall crawler mechanism.
The ball shooters that shoot on the ground as opposed to in the air.
My strategy is mainly offensive. What I plan on doing is flipping my opponent over so that they can't score any more points.
So I have the arm, which the balls go down the arm and shoots the balls into the hole. At the same time, I'm collecting the balls.
Ball shooters of the kind I designed go all over the place. Different times they shoot different distances and different directions and all kinds of stuff. And that's Tiger Woods doesn't score in golf by launching balls all over the place. He's pretty precise.
I feel that there's a very small chance in winning the competition. And because of that, I didn't focus my energy on a machine that could win the competition, but a machine that would teach me a lot in the building and designing process.
And at the same time you're doing your concept, we want them to do first-pass physics. Is a ball shooter possible with the power and the motors you have? Do you have the tractive force you need? Can you climb that hill? Because a lot of times people create these wonderful concepts that isn't physically realizable. So we introduced that physics is a very, very powerful part of concept generation.
And this is where your background in math, science, and engineering comes in handy.
Kinematics,
lift,
balance,
conservation of mass,
statics,
energy,
forces.
For every one force, there's an opposite force.
Traction,
energy,
normal force,
kinematics,
torque,
and speed.
And how can I simplify the physics?
The first rotation is the one that is the hardest, because I'm torquing a 1 Ford motor, all the materials in the last 3 modules, and the Bosch motor. So I had to do all the calculations to prove to myself and to my professor that it could be done.
Don't think that you can cheat the physics, because
physics rules. The next step is, now that you have an idea of what you want to do, create concepts, paper drawings, cardboard.
I really used the sketch process as kind of a filter, where I poured in sort of all the ideas that I thought of, that I'd really like to try, but probably wouldn't have enough time for, and then began to sort of cull them so that I got down to what I could do in the time with the parts allowed.
The sketch process is very important because you get a lot of problems right out at the get-go. You don't want to be out of the size constraints or have 2 pieces that don't fit together because they're at different angles. Those are things you could be able to work out. Once you draw it, you say, oh, well, that's kind of impossible. Do I know how to make that?
Originally, I started off with just a general isometric sketch. Eventually, I moved into a bill of materials type sketch, gives you a little more detail. Then eventually, I turned into this, which is a full module sketch.
From there, I moved on to a design very close to the one that I finally adapted, where, again, you have the wall walker and just a basket, really, inside it, and an arm that sticks out to that center chute, where the balls just roll in, you collect them in the basket, and then you actually, instead of having a ramp, you drive back over to the 2-point hole and just drop them through.
This is a picture of what I want to make. The balls are stored in here and a door opens and they all flow out. It starts in this position and expands out once the contest starts. And to get the height I want, I've also arranged it so that the pistons will push up that base and lock it into place. After I finished designing what I wanted to build and drawing the pictures for it, I actually built it. This is my cardboard model. And this helped me not only in structural elements and making sure that the base would be very sturdy, but also in size constraints. And I ran this on the table and filled it with balls and found out that as soon as I come up, all of the balls just jam. And I have to fix that. That's a major problem.
Now that the basic elements of the design had been worked out through the sketches, I built a sketch model of the module that I was most uncomfortable with as far as the physics were concerned.
And this is actually the sketch I used to build my sketch model, which I have right here. Basically, I decided to build a more complicated sketch model because I figured I could probably get away with putting in a lot of effort early, and if I built this cage very well and tested it out and it worked, then I could just transfer this directly to my machine.
As you can see from this, I really didn't spend as much time on the sketch models as many of my peers. That was because I wanted to move quickly to a computer-aided design format where I could nail down all the parts, all the nitty-gritty details before I cut any parts or did anything else in the shop. This is the model that I created. You can see here the ramp that collects the balls and then also the drive module. Now, creating this model probably took approximately 50 hours, but enabled me to test fits and to refine the design outside of the shop, and so it probably saved me 2 or 3 times that when it actually came down to cutting metal.
From that conceptual model has come your layout. The machine then in that layout form, we have them identify what are the prime modules. What are the critical technologies that if they don't work, they're in deep, serious trouble. And once you've finished the hard thing, you go and you just start building the modules one by one, starting at the hardest, working down to the easiest. And what you'll find is that the machine just slowly evolves and builds and morphs. And then, boop, you have a real engineered 2007 machine ready to seriously nuke glutes.
To me, the biggest surprise during this whole process was actually finding out how much effort goes into making something as simple as a little 2007 machine, the amount of sheer effort it takes to put all those mechanical pieces together to make them work in harmony perfectly.
I have to think of a way of having wide flats.
I plan to just drive out as quickly as possible and drop these gates here. And as those gates drop, to allow balls to roll straight into the machine and shoot them directly to the hole. The challenges that still have to be met are, one, here in the bearings, my shooting module is just a little bit too wobbly. So what I have to do is go re-engineer some bearings and press fit them into the hole so there's no movement. As far as the jamming problem, I think that if I put more curvature on each of these welding rods to round it out a little bit more. And after that, I think I should have my perfect machine, hopefully.
I come in every morning at 7:30 because this is the best time to work. There's nobody here. And all it needs to stop. Once it piles up with balls, there's a certain number of balls it can take before it won't lift.
Okay.
And I want to make it that no matter how many balls go in there, it will lift, which just means for now adding another spring.
But the biggest headache as far as adjusting the machine to fit the table really had to do with the arm, because I had a lot of trouble getting it so that it came to the right height on the on that little chute that sticks out from the table. It would either be too high or too low. The balls would run off, or they'd hit the front of the ramp and not roll on. That probably took me about 3 or 4 days to get right.
There's 3 ways you can engineer the distance which the balls travel. And first is the distance the rollers have between the rollers. The closer the rollers are to the balls, the more compression you have with the balls, the farther the balls could go. Also, the material you have on the rollers. You could go for more friction like rubber, or you could go for less friction in terms of just having the rollers plane. And also another way is how fast the rollers go. And playing around with those 3 ways, I was able to get the distance I needed.
But the coolest thing I think about this machine is just the way it can extend out. And there you go, voila, 6 feet.
It's common knowledge that keep it simple is one of the key issues to do well in 2007. But then they just get caught in their designs, they get carried away. It happens to me, it happens to all the instructors. They have nice designs, you try to keep that going. And it gets a little more complicated than you thought it might get. But, that's just how life is.
A lot of my students would sit down with a piece of paper and decide, oh, I'm going to do this, I'm going to make a car, and I'm going to have another car that's going to drive out from underneath it, and I'm going to have a conveyor belt, and they wouldn't really listen to me that I said, that's going to be a lot harder to do than you think it is. And they'd start machining and realize, wow, that is a lot harder than I thought it was.
The most ambitious design that I have seen was one that would go for all 5 balls at a time. It's been so ambitious that the person who is trying to build it is not done yet.
I think one thing I do differently is maybe try and go for something a little bit simpler but more reliable.
I think some of the most important factors in being able to succeed are time management and a realistic sense of what you can and can't do.
I like Sarah's machine a lot. It's intricate, it's complex, but at the same time really simple. I'm just fascinated by the way she designed it, and she's building it right now. I just hope she gets it done.
I think if I can get it built, I'll do well. It's just a matter of having enough time to debug. I'm a little stressed. I'm going to be in lab many hours next week.
One of the front runners that I've seen in the class so far is a girl who has a machine that it drives up underneath the center ridge, and it covers all of the area where the balls are falling.
And I'm going to try to collect all 4 of the balls coming down from the volcano into my bin, and it's going to shoot them out simultaneously to the 1-point hole. Originally, the size constraints did not allow me to do this, but as I developed my strategy more and more, I decided that I was going to go under the ramp and try to prevent everyone from getting their balls.
I actually have a student in my class who might possibly be able to overcome her. He has a forklift mechanism at the front of his machine, which he puts underneath machines and then tips his machine back, and they flip right over.
And then, depending on my opponent, some of them I'll attack, some of them I won't. But the ones that I do attack, I'll drive over to their side. And when I drive over there, I'll open up the claws and lower the arm, and then try to drive my machine under theirs. And then I'll lift the arm up and try to, while I'm driving toward them, and try to topple their machine over. I'm planning to go kind of nice on most of them. Just the ones that score a lot of points are the ones that should watch out.
We've got a bunch of machines that have been designed. They start over the hole, and then they run away, and they drag behind them the chutes, and the balls fall into that. The little motors go, ball spitters.
The driving mechanism worked, the ball acquisition mechanism worked, but the shooter module did not work. Because when it was initially shooting, it was shooting the balls way too far. And to compensate for that, I turned down the power by about 75%. And that turned it down too much, so you saw the ball start to jam. And basically, I'm stuck with a car full of balls and no points. So Considering that my in-house competition, which determines my seed for the final competition, is in about 15 minutes, I'm just a little bit nervous about what I can do.
I think a wall crawler actually has a pretty good potential of getting a lot of balls if it's done right. I haven't seen any wall crawlers yet that do it right.
So during the contest, my robot is going to be dividing up into 2 separate modules. The lower module, which you can see here, is called the annoyance bot. While this robot is trying to disable my opponent, the upper half of the robot, the wall crawler, is going to move across the wall over to where the conveyor is and start collecting balls and funnel them back to the low point hole.
Basically, it's a dump truck. When it's down like this, it catches the balls from the volcano and they roll in and fall into place in the bin. Then I drive over to the 2-point hole and actuate the bin, which brings it up. It releases half of the balls this way, and then I bring this back and release the other half. That way there's no jamming problems.
I built an arm that would reach out to the end of the volcano. As the balls came in, it would fall into the arm, right down this channel, and down this other channel that I built into my hole.
Oh, I like the guy, well, I like them all, actually.
There's no doubt some of these are going to be really cool. All of them but one will lose the contest.
The kids are having a lot of fun. They've finished all their building, a little bit of tune-up here and there, put a little bit of lubricant here, bend that little flap over so it'll fit in the box. And they're testing, they're driving, they're getting their scores, they're going back to do more. They're seeing what their friends are doing, and they're developing new strategies. So this is really just before you put your product in the box, give it to the shippers, off to the customer.
There's 8 hours left to go, and you see some students who are frantically trying to finish their machines and some students who are just trying to get onto the tables to practice. Some of the people who haven't quite finished yet are people who had extremely difficult designs, and they knew it was going to be hard to manufacture from the start, so they knew this was where they were going to be.
I've been in lab all of the last 3 days. Tuesday and Thursday I had to go to my humanities class. But aside from that, I've been in lab every day. I'm reaching the end of my chain. But I can sleep in tomorrow.
I'm really happy with the machine. I mean, it might not work during the contest, but knowing the amount of effort I put into the machine and the amount of commitment I had with it, I have this certain bond with it, so.
Even if it doesn't really work quite right, just having built something that's cool, I'm really satisfied with that.
Sometimes I like it. When it doesn't work, I don't like it very much.
And then in 10 days, it gets to the customer, which is them on the other side. They take the machines out of the box, and the boxes are shipped across campus in the back of a pickup truck, so they're rattling like this. So anything that's loose that isn't well engineered is going to fall off, which voids the warranty, but that's their problem. That's why they had to engineer these machines. And then they get a couple hours to drive their machines, to take them out of the box, set them up, tweak, put the belts back on, and then the contest!
This is 2007, License to Design. This is night 1 of a 2-night celebration where the students get to show their engineering prowess on our fun tables here.
So, Mark, would you like to tell us what design is all about? Okay, I'll do that. It took several weeks to reach the peak, but now that the designs are tweaked, the actions speak for themselves. Parts off the shelves were limited. Dig into a box, start a model, then finish it. Design takes time, so I start mine early. Can I be afraid to get my hands dirty? It's time. It's time. If something isn't made already, then I will build it. No mountain is too high, no any road is too long. If it doesn't break my spirit, it will only make me stronger. I congratulate all who have created. May your work be appreciated. Hold your head up high because you made it.
Mark, we are ready to start on blue and orange. Contestants ready? 3, 2, 1, go! All right, judges count. Go!
Oh, span it.
San, ni, ichi.
All right. Thank you, Violet. That was wonderful.
I didn't do quite as well as I thought I was going to. I got eliminated in the first round by disqualification, really, because I didn't take one of the rules as seriously as I should have, and I was actually just barely touching the top of the wall, where if I'd put just sort of a 16th of an inch of material under one of my supports, I would have been fine. But I got to run once, and then, you know, it was satisfying.
Go!
Well, as soon as I saw that I was going against, his name is Colin, I knew I was in trouble. Well, what really worked was the shooting part. I mean, I was able to get shooting exactly where I wanted to shoot. So I knew I was going to have trouble with him pushing me out of the where I was collecting my balls, and exactly what he did. If it wasn't for him, I think I would have gone pretty far.
If I were that dump truck, I'd get over there and get some points.
I didn't count on too many people trying defense, and basically he got a ball in and then came running after me. The contest is just a lot of fun.
Iman, Munanke, Pa, go!
Yeah!
My girlfriend brags to her mom and dad about, hey, my boyfriend got in the top 8 machines out of 140, you know.
I always knew my vulnerability was how light my machine was, and that's basically what my downfall was tonight. Tonight was great, and great. A little tense, but it was all great. My final competition, incidentally, was against a very good friend of mine, a girl who lives on my floor. Basically, her machine is strong, and my machine is very light, and she pushed me out of the way. But we just couldn't get out there in time, and she won. It was a good battle. It was fun. When you see someone else's machine do well that you've seen go through the process, it's just as justifying as seeing your own machine win. That's how I'm feeling right now.
2, 1, go!
Basically, the first torque shifted my machine out of position. And then he came with his small car that basically is meant to push you out of the way. And once it's out of position, my machine is useless. So in the first 5 seconds, I lost the contest.
All right. All right. I have no idea who's going to win this contest. This is one heavy-duty contest.
Uno, due, tre, avanti.
Designer Dopper Stopper is stopping Designer Doppin.
The thing that I got the most excited about was the crowd yelling and screaming for you. It's like a sporting event almost. I'm a mechanical engineer. Kind of ashamed to admit that I lost to an electrical engineer, but that's okay.
Oh, the shaker mover is shaking and moving.
Experience. It was tough for a while. I was in lab all the time, but it's all worth it.
Yeah! Colin just needs to get one in. He's got him in. Oh, yay! Colin Boswick seems to have won it. MIT ME 51898 2007 number 1. No other letters required.
The most unbelievable course I've ever taken, and one of the most fulfilling experiences of my entire life.
This class does such a great job in teaching you all about design and manufacturing that 2 years ago, a Harvard student was taking the class and actually managed to come in second in the contest. And Alex Slocum at the end of the contest made the comment that this just goes to show you that we can teach even a Harvard student to design almost as well as an MIT student.
One of the most significant things I probably really took away from this was that the devil is in the details, because one small screw-up can take away all the effort that's gone into the whole machine.
There is a difference between engineering and coincidence. Engineering entails planning, it entails using your mathematics and physics to predict what is going to happen and to use this predictive process to design for success.
I mean, this class taught me that my ideas can become reality.
Guidant is a company committed to creating innovative therapeutic devices that make a positive difference in patient outcomes. Around the world, our products help patients return to active, productive lives. There is a common bond among Guidant employees around the world, a bond forged in the value of the products and services that Guidant provides, developing innovative technology to save and improve lives. Guidant.